I would like first to answer a bit better Javier's question yesterday. So I was saying that, so this is related to the dynamics of, so we have a Hamiltonian that is k-local and has a bunch of, has terms which roughly are of this form. And then, well, this could be sigma matrices and so on. And then we discussed, let's say these are like, could be like Majorana fermions. And then we discussed that we had dynamics which could be represented as this tree. And so after each time step, we had an exponential growth in the operators. And then I described this as arising from the one commutator with the Hamiltonian, and said that this was like two commutators on the Hamiltonian. And this was slightly wrong, and that arose, that gave rise to a question, which was by applying, it looks like you need to apply the Hamiltonian n times to reach n particles. So more correct way to say this is that each step in this figure represents the action of the evolution by one time step. So let's say that U is the evolution of the total system, but by essentially one time step. So this is equal to e to the I delta t times h, okay? Now we started with, let's say, fermion number 1, and this gave rise to fermions number I, j, and k, okay? Now, in this unitary operator, well, we have a Hamiltonian which contains many, many terms, and there will be only a small subset of the terms that will act on fermion number 1, and we'll give these terms here. When we act in the next step, the Hamiltonian, so here the unitary operator can be split, so there are different terms here in the Hamiltonian, and there will be some terms that act on fermion I, some terms that act on fermion j, and some terms that act on fermion k. And to lead in order in n, all these terms are different. So we can think of the Hamiltonian as a kind of product of the unitary operator, sorry, as a product of the three, of the one that contains the terms in the Hamiltonian that act on one, and so on. And so then, when we act with the second time step, then each of these U's will act on each of the fermions and will give rise to the rest of the fermions, okay? And so in this way, this unitary operator is acting on all of them at the same time, and we get this exponential growth, okay, in the number of operators. Okay, so that was the answer to that question. Okay, so are there any other questions from, yeah?
Why from the initial point you already begin studying fields with the finite temperature? I mean, for me, out of the field.
Yeah. Yes. Yeah, maybe I should also mention one more point that people ask me afterwards. So here when we discuss, this picture of the evolution is really applies for infinite temperature. So where you take one operator and we have this whole evolution. When we are at finite temperature, or even lower temperatures, let's say even 0 temperature, so we have some kind of projection onto lower energy states. So even though we have this features for operators, when I mean this is like the evolution of the UV operator. But if we then take that and we focus on an infrared operator, so some operator which acts on the infrared degrees of freedom, so the degrees of freedom at temperature T, we have to smear this a little bit. And then it might turn out that some of the operators that appear here are acting on high energy states. They connect high energy states and so on. And all those somehow should be projected out. And so the dynamics when we are at finite temperature is occurring on a smaller part of the Hilbert space. And we should, in principle, so we could, one way to analyze this would be to first focus on the effective dynamics at that temperature and then think about the evolution of operators within that subspace. So if you go to 0 temperature, that's an extreme version of the projection, and there there if you act with any operator, so you can go into higher energy states than the ones you had originally at 0 temperature. Okay, I'm not sure if I'm. Yeah. So in this whole discussion of chaos, the idea is that you act with some operator that transforms one set of microstates into another set of microstates that are completely equivalent and have the same energy. Right? So they're essentially indistinguishable from in an average sense. It's only when you compare them that you can distinguish them. Okay. Any other question? Yeah, I wanted to make another point related to last lecture, which is that we saw that we emphasized the fact that we related this chaos to the dynamics of gravity, which is essentially was in the classical regime. And so it seemed like some very quantum property, chaotic and messy, got related to something really simple and geometric. So there is another example where something similar happens, which is if you consider motion in hyperbolic space. So imagine you have hyperbolic space. So this is just a particle moving in hyperbolic space. Then in this case, so you have some trajectory, and if you do small perturbation, will have some other trajectory. And in this case, the Lyapunov exponents are just fixed by the geometry of hyperbolic space, and of course the velocity of the particle. But it's one case where Lyapunov exponents are fixed by the geometry of where things are moving. Now this system has infinite entropy, but you could consider a Riemann surface where you make a quotient by gamma, and then you'll have this feature for a while, and then you'll have here the fundamental region of the Riemann surface, and then these particles will come back in, and so on, and we'll have still, and these systems have this chaos. Okay, so. No, this do not saturate the bound. Yeah, to make the bound apply, you have to define carefully which operators you define, and that hasn't been done. There was a paper by Kusher Krushan, I forget his precise pronunciation. He noticed that when you are approaching the bound, the wave there is a spreading of the wave function cannot be approximated as classical, as I have done here, and there is some kind of spreading of the wave function, and that might be enough to saturate the bound. But the calculation was not done of what exactly the Lyapunov exponent is in these cases. Okay, so some comment. Good. So now today we are going to discuss. Today we are going to discuss nearly ADS2 gravity. So. So this is a particular simple gravity theory which describes near extremal black holes. And the objective of what I'm trying to say is I'm trying to describe this gravity theory, show it to you how simple it is, and then try to fit its relevance, why it's relevant for various physical problems, and perhaps say some words about the connection to the SYK model. So this gravity theory was originally introduced by Teitelbaum and Yakiv, studied by Almeri and Polchinski. We wrote a paper with Stanford and Young, and also Kitaev made some further comments. And then there were many other papers on this subject. So before we talk about nearly ADS2, let me just discuss some features of ADS2 gravity. So let's ignore the word nearly, and we start ignoring it first, and then we'll run into some problems, and then we'll retreat and say that we have to consider nearly. So ADS2 gravity naively would be described by an action which is some constant times square root of g r in 2 dimensions, right? And if you start with this action, you can calculate some things like the entropy of the black hole. So imagine you have, let's say, a Euclidean configuration, which would be let's say, hyperbolic space, so H2. And so this has a periodic Euclidean time direction. You view the angular direction as time. And you can view that as a Euclidean black hole, and you can calculate the entropy, so S0. The extremal entropy, which is essentially 4 pi, this phi naught. Okay? So it comes basically from the Euler. Well, this is, yeah. For that, we need to introduce here a boundary term. So here is integrated over the two-dimensional surface, and this is over the boundary of the two-dimensional surface. And this term, you always need this term in the gravitational action because you have terms with two derivatives here. And so in order for the variation to be well defined with boundary conditions which fix just the metric and not the first derivative of the metric, you need to add this boundary term. This is true in any number of dimensions and also in 2 dimensions. And well, when you take this action, you get a simple answer because this answer is the Euler characteristic of the disk, and which gives us the factor of 4 pi. Okay, this is just the standard. Yeah. Okay. Now, one feature of this action is that it's completely topological, so it essentially has no dynamics. And even if we add matter, so if we take that action, so phi naught square root of gr plus 2k plus, let's say we have some matter action, which includes some other fields and the metric. This, for example, the integral of chi squared plus, let's say, m squared chi squared. So integrated over 2 dimensions. So here we have simply a scalar field that propagates on that background. So we have something like this, and we calculate the equations of motion for the metric. The equations of motion, this piece will not contribute anything to the equations of motion because it's topological. We can vary the metric and we get the same action. But that piece will give us a stress tensor of matter. So we'll have the matter stress tensor, T matter, mu equal to 0. Okay? So it's setting the energy of the matter to 0, so we can't do anything. We can't produce any excitation. Okay? Okay, so that's from the gravity side, and then we can.
The entropy, where it comes from, doesn't have any.
Yeah, that's a good question. And I will not. Well, yeah.
Why is it that you didn't include the cosmological constant?
Yeah, so we could here add a cosmological constant term. Well, I'm first going to consider this theory without the cosmological constant. We could have included the cosmological constant term, and then here in the equations of motion, we would have obtained a term like this, but still is set in, well, first of all, we would be forced to have some matter, right? And of very specific kind and so on. I think I'll later give a slightly better discussion of this point. So, you essentially, in order for this to work, you need to have here some scalar field potential that will cancel the cosmological constant term here. Okay, so this still continues to impose that t plus plus, t minus minus is equal to 0. So it doesn't allow matter, ordinary matter excitations. So now, so this is from the bulk point of view. From the boundary point of view, if you imagine that there was an ADS2 CFT1, right? So what would be a CFT1? So that would be some quantum mechanical system that has a scaling symmetry. And then you could imagine that that quantum mechanical system should have some density of states. And the density of states has to be compatible with scaling symmetry. So this is something that we integrate over energy to get the number of states. And the number of states is scale invariant. So the density of states has to scale like 1 over the energy, or have that kind of scaling. And two possible things that are compatible with scale invariance are delta of E. So that these are two functions you can think of that are invariant and they're rescaling in the sense that they scale covariantly with like 1 over energy, right? Now, these two have a problem. If you have this one, then when you integrate over energies, you do this integral, you'll get the divergence from small energies. And small energies are precisely the energies where this is supposed to be valid, so you get some infinity. You would have an infinite number of degrees of freedom. That's one possibility. The other possibility is to have the delta function, but then you only have zero energy states. You don't have any excitation. So that's similar to what we had over here. So really this, so ADS2 CFT1 really does not make sense. So you'll see these statements in many papers, but it does not make sense as the dual of some theory with finite entropy and so on. So any paper that talks about this and does not apologize for this has some problem. Now, there are many papers in the literature that talk about the ground state entropy, so just purely the entropy itself. So for example, Sen and collaborators and so on have written many papers on this, and that's perfectly fine. So that, and they found lots of interesting structure related to the entropy of BPS black holes, and they can get it from quantizing actions which contain these plus, so they're exactly ADS2 plus some internal dimensions, and depending on the internal dimensions, you get the entropy and even 1/n corrections to the entropy, or sometimes even non-perturbative corrections to the entropy. So I won't discuss that here, but there is a nice story about the exactly zero energy states, and for that story, you will not need anything, any of the things I'm going to talk about now later. So, but all those things are kind of focusing on purely the zero energy states. They don't have any dynamics. And if we want to include any dynamics, like something falling into the black hole and so on, then we need to do a little bit more. We need to go to nearly ADS2 gravity. Okay, so in this theory of nearly ADS2 gravity, we add one more field, and so we have an action which contains the term we discussed here. Let me call that S0. Whose role would be to give rise to the extremal entropy of ADS2. It's called extremal because ADS2 is related to extremal black holes, as I will discuss later. And then we add one more field, phi, and we write this particular form for the action. So this is the bulk integral, and this is the boundary term. So boundary of sigma 2. Now this looks like some arbitrary term, but later I will justify that this is the. For now, take this as an example of some theory, and then I'll explain why this is the one that describes nearly ADS2 spacetimes in most situations. So in this theory, there are actually no propagating degrees of freedom. So when we calculate the equation for phi, that sets the metric to be exactly ADS2. This is like a Lagrange multiplier that sets the metric to be exactly ADS2. And then even if we added matter, so if we add matter, so here when we add matter, we are going to imagine that the matter only couples to the metric and not to phi. Justify that later also. And in that situation, again, the metric is exactly ADS2, it's a rigid, so we get a rigid ADS2. And then when you calculate the equation of motion for the metric, you get the term that is the same as the matter stress tensor we had before. But now you also get the contribution from phi. So contribution from phi is linear in phi, and I'm going to call it the stress tensor of phi. And this has the form of differential operators acting on phi, right? Maybe some constants. And so here you can analyze this equation, but you just say, well, I have some matter propagating in the bulk, and then I solve for phi. Okay, solve for the value of phi. And it fixes, these equations fix phi up to some small number of integration constants. Okay, I will discuss later. So phi gets completely fixed. All the sort of functional degrees of freedom of phi get fixed by these equations. So So here you have basically 3 equations for phi, and they are compatible due to the conservation of the stress tensor of the matter. Okay, so that's this action. So I explained a few properties so far, but now I'd like to explain why this action is the relevant action. So why we want to consider this action. So imagine that you have some black hole or any system in higher dimensions, but you do a spherically symmetric reduction. So you focus on. Is there a question? Or? Yeah, S0 was the piece in the action that was phi 0. Yeah, S0 has an ambiguous meaning. Like it could either mean the ground state entropy or this term in the action, right? And the only role of this term in the action is to give rise to the ground state entropy, nothing else. So we can forget about that term for a while. Okay, so now we want to have, so we consider the most general spherically symmetric reduction of gravity to 2 dimensions. So that the 2 dimensions are time and the radial direction. And we imagine we have some extra dimensions, but everything is symmetric in the extra dimensions. So the most general reduction will be an integral over 2 variables, square root of some metric, which I'm going to call g tilde. And then we can have general functions of phi. Phi is something that measures roughly the size of the extra dimensions. Since I'm not specifying what they are, might be a general function. I'm not even saying exactly what phi is. Plus some other function of phi tilde. So there could be kinetic terms for this phi tilde. And in general, also, there could be some potential terms for this phi tilde. So here we're keeping the degrees of freedom, which are the metric, and somehow the size of the other dimensions. And now we can basically call this term here phi, okay? And then we can redefine the metric g tilde to be some function omega of this phi squared times g, so g mu nu. And the effect of this, so this term will cancel out in here, but it will give rise to a term that also has some gradients of this function, and we can use that to cancel this term in the action. Okay, so we choose omega to cancel this term, and we have one free function here. It's enough to cancel this function here. And in the end of the day, what we get is the integral of d2x square root of g tilde, square root of g now, phi r, so that was one of the terms, and then plus some function which we will call u of phi. This is okay, so the conclusion of this is that up to field redefinitions, this is the most general action that comes from spherically from some spherical reduction. So this is valid for the Schwarzschild black hole in any dimension. It's valid for charged black holes in any dimension, and so on. So you can always do this for p branes and so on. For dp branes in, let's say, the d0 brane black hole in 10 dimensions and so on. Okay, so that this is the most general action. And now we can have different U's. So first, consider simplest case is u of phi equal to some constant. Okay, that's related to the question that Gishe was asking. So let's say we take this to be a constant, and in that case we have an action, well, phi plus this constant. And here now the equations of motion for phi fix the metric to be flat. So the metric is completely flat, and then the story will be similar to the story we are going to say for ADS2, but instead of ADS2 we have flat space. And that's something that was studied a lot in the 90s under the name of dilaton gravity. They were writing the action in slightly different variables, but it's completely equivalent to that story. Yeah, okay, so that's that. So the next possibility is to say that u of phi is a constant plus phi, right? Plus, And well, let's say it's equal to phi. So let's say it's a constant plus phi, but then we can redefine phi so that if we redefine phi so that u is just a constant, this term will give rise to, we just shift the, that will just shift this phi 0, and we are forgetting about phi 0 anyway. So we can just simply say that u equal to phi is the next case that we would like to consider. So the next case we consider is this one, and that's the case we are considering now. And then you could, in addition, have some other terms like alpha phi squared and so on. And this would be corrections to what I'm going to say. I'm going to ignore these terms for now. Now, why is it reasonable to ignore those terms? Well, let's see how this type of problem arises if we come from higher dimensions. So imagine that we have a charged black hole, in, let's say, 3 + 1 dimensions. So far away, we have R1, 3, okay? And then we have some black hole here. Now, charged black holes, in order to avoid singularities, we need that the mass should be bigger or equal than the charge. And the case when the mass approaches the charge, or is equal to the charge, so this case is called the extremal black hole. And that black hole develops a symmetry in the near horizon region that, in which the near horizon geometry is AdS2 times S2. Okay? So it develops a scaling symmetry. So there is a, if you focus on the near horizon region, instead of having just simply the time translation symmetry, which is the only symmetry that all these black holes have for generic values of the mass, for this special value of the mass, we also have a sort of shift symmetry in the radial direction, essentially, or a scaling symmetry plus some other special conformal symmetry. So this has so-called SO1-2 symmetry, or sometimes called Sl2R. Okay, very good. So that's this case. Now, in this case, so when you go deep into this extremal case, the area of this S2 is some value. Let me call it A0. That's the extremal area, and that determines the area, the entropy of the extremal black hole. As you connect into this other region, the area starts deforming away from the extremal area. So we have some delta of area, which depends on R and so on, of the radial direction. And the idea is that when you analyze the dynamics of gravity in this region, this type of terms in the action, this effective action that we are discussing arises in this context, and A0 it plays the role of phi 0, and this delta area, the deviation from the extremal value, plays the role of what I was calling phi. Okay? So this is the connection between the formalism we are talking about and some higher dimensional discussion. In other words, this theory describes a certain sector of the bigger theory. Okay? Now, when we consider matter propagating on this background, so the matter will be sensitive to the properties of, the matter will be sensitive, for example, if we have Kaluza-Klein particles moving on S2, it will be sensitive to the radius of S2, but to lead in order, we can ignore this small correction. So we're going to be in the regime where delta A is small, and so to lead in order, we can think of the matter as not coupling to phi, which is that small change in the area. So that's the first approximation. Then there will be other terms where there will be extra couplings to phi, but they are suppressed by factors of phi or phi 0. So in this physical context, we will always think that phi is smaller than phi 0. When we talk about this effective theory, we can even forget about this term and just talk about this action. Okay? And that's what we are going to do essentially from now on. So this whole discussion was basically just to put this action in some context, of some higher dimensional context. It's not just a simple just action we pull out from a hat, but it arises as a limit of some more interesting, more general situations. I mean, one problem that I think might be interesting is to understand whether this action also arises for the case of the Kerr black hole in 4 dimensions. That hasn't been shown completely explicitly. I expect it to be the case, but as far as I know, has not been shown explicitly. Okay. Now, so I was discussing, so that's, we end the discussion of the relevance of this action. We now are going to start analyzing some aspects of the dynamics of this gravity theory. Yes?
Are there models where you can change the radius of the S2 compared to the ADS2 cosmological constant? So you can create a hierarchy between the masses when you do this dimensional reduction? Or you always get that they are comparable?
Well, the simple examples like black holes and so on, they will be comparable. I don't know if of examples where you can make them arbitrarily smaller. I mean, you could start, so there are some limits of ADS3, for example. So if you had an ADS3 and then you have ADS2 times S3, then you could imagine trying to make the size of the circle, let's say of the ADS3 circle, string size, for example. And then you would have an ADS2 times a string size circle. So that you can get from a WCW model with the appropriate central charge. That's an example. But I don't know what would be the dual in that case. Okay, so let's go back to this action. And here we started discussing the equations for phi. I said this contains terms like gradient mu of phi, plus some other linear terms in phi. And we can use it to solve for phi. Now, let's first consider the simplest solution. So we set the matter equal to 0, so there is no matter. And so in that case, it turns out that you can in general show that epsilon mu nu d nu of phi is a Killing vector. So for any possible solution of this system, if you construct this, the equations of motion for phi that we have there imply that this obeys the Killing equation. And so the solutions automatically always will have a U1 isometry. And so we can choose, and it turns out that points where the gradient of phi is 0, those are points of fixed points. And generically, the solution will have one such fixed point, and so we can choose it to be at the origin of the coordinates. And so we can have solutions which look like sinh of rho squared d squared. And here the plus and minus refer to either Euclidean time or Lorentzian time. Okay. And then in these cases, phi is equal to some constant, which we are going to call phi h, which is the value of phi at the horizon, so at rho equal to 0, times cosh of rho. And then any other solution turns out to be a limit of this solution or an analytic continuation of this solution. But these will be the solutions we are going to be interested in. They describe a near extremal black hole, so some finite temperature configuration, and where phi, remember, was the deviation from the area from the extremal value. It's growing as we go to the large rho region. So now, in any of the systems, we need to put some boundary conditions. And in the usual boundary conditions that we would like to choose, well, they can be motivated in different ways. So one can motivate them by saying that, well, we join this region into a bigger space, right? And then we'll have to put some boundary conditions there. And the type of boundary conditions that arise from that kind of analysis is that you want to fix the metric along the boundary direction. So this is, means the metric along the parallel directions, so along the boundary. Or this is equivalent to fixing, so we want to fix this. This is the same as fixing the proper length of the boundary. Proper length or time. Length or time. I mean, length is in Euclidean space, in time in the Lorentzian signature, of course, along the boundary, so that it's going to be fixed. And also, we want to fix the boundary value of the dilaton to be some phi b, okay? Some boundary value that we fix. So that's it can be motivated from the extra dimensional discussion by saying that, well, when the area gets to be to a certain point, I will join to the bigger space, and so it's convenient to fix these boundary conditions. Okay, very good. Okay, so we have this general solution, and so we can draw. So these are some coordinates for ADS, but it's also useful to think. So I'm going to here think about the solution for the Lorentzian case, and it's useful to draw the whole Penrose diagram of ADS2, and then these coordinates cover just one sort of Rinder type wedge of this Lorentzian diagram, and then there is a sister or partner wedge here on the left, so there is the right and left wedges. So in these coordinates, the surfaces of constant rho have this form, and so time runs along this direction. So the time translation symmetry here acts as a boost around this point. And here on this boundary, phi is going to plus infinity. So here, phi is equal to plus infinity on this boundary. Phi is equal to phi h here at the horizon and then along these horizon surfaces. We could continue this diagram here to the future. Phi is equal to minus phi h here. So for that, you need to analytically continue those coordinates. I'm not going to do that explicitly. You can believe me about this. And here in this boundary, so phi is equal to minus infinity. So I'm just simply analytically continuing the solution, also minus infinity here and plus infinity on this boundary. Now, if this you view this as coming from the higher dimensional black hole, so this would be joined into a flat space region, and here we would have the singularities of the Reissner-Nordstrom solution. So, for example, the charged black hole solution. Now, here, well, we have this region, and we don't know exactly what goes wrong with this action when phi goes to minus infinity, but we think that that's probably some kind of singular region. So most of the discussions will focus on these regions of the geometry. Would be interesting to understand self-consistently in this action how to deal with those type of these regions. Okay, and within this region, there is a place where phi is equal to phi b. So here, phi is equal to phi b. Okay. So we should think of the real space-time as whatever is within in the region where phi is less than phi b. Okay. So phi b, we're going to take a large value, and then so we're going to say that phi b. We can here do the usual so-called holographic renormalization, where we take phi b to be some renormalized finite value times some epsilon, and then we take epsilon going to 0, and we take the metric along the boundary to be, let's say, dt squared, where t is the boundary time. But let me call u the boundary time divided by epsilon squared. So we can fix the metric to have this form near the boundary, where we keep u and phi r fixed. That those would be, this is the boundary time, and this is some kind of renormalized value of the dilaton. And then we take epsilon to 0, and we can remove epsilon. So that's what we will do. But it's useful for thinking about the problem to think about this, but keeping epsilon finite. Now, so this is the solution without matter. And if we add some matter, let's say we added some matter here, we send in some matter. So we come back to this equation, and we can solve. First, this is a linear equation for phi, so we can write it as the superposition of two solutions. One was the solution we had before, right, when matter was 0. And now we add the matter, and so that will change the solution for phi. We'll add a new term for phi in this region. Okay, so in this region, we'll have a new term for phi. And what that will do is it will it will change the value of phi, so now the surface phi equal to phi b will not be this original line, but it will be some other line that we could calculate by first solving the equation for phi and then calculating the position of the new line. Okay? And so you could do this, and in this way you can understand somehow the gravitational back reaction of this particle falling in, that before the horizon was here, and after the particle falls in, the new horizon is along this line. So that there is some region that before you could see, and now you could not see anymore. So this is somehow the growth of the horizon, if you wish, or the motion of the horizon when you send in some extra particles. So the reason I'm saying this is to emphasize the fact that that even though this action has no propagating degrees of freedom, there is a gravitational degree of freedom associated to the position of this boundary, and that's where all the gravitational effects lie. So all the gravitational effects have to do with the position of this boundary inside the rigid ADS2 spacetime. Okay? So this is similar to ADS3 gravity. So some of you might be familiar with ADS3 gravity, where again there are no propagating degrees of freedom, and all gravitational effects have to do either with quotients of the space or with perhaps some boundary degrees of freedom. Some boundary gravitons. So in this case, there is you can call this a boundary. There is some kind of boundary graviton. We'll start discussing its dynamics a little more precisely in a second. So for now, I've just given you the dynamics that comes most obviously from this action. Okay. So now I'm going to give some other ways of thinking about these dynamics. We'll see two more ways of thinking about these dynamics, and each of these two ways has some advantages. So it's somehow some simplification for analyzing the dynamics of this theory. So this is the most straightforward that you would think about by writing this action, but there are some other ways which bring out the simplicity of this model more clearly. Okay. So the first one is the following. So we can think of, we go back to this action, and we integrate out phi in the bulk, and that sets the metric to be ADS2. And it sets also that term to 0 in the action, so we end up with an action where we have an ADS2 metric, a fixed metric, and then an action which contains this extrinsic curvature term. Now we write this extrinsic curvature term as, we write it as the Euler character plus, in order to write it as the Euler character, we have to add the curvature term. Okay, well, maybe I'll do it in two steps. So we have square root of g, and then we act with square root of g, the curvature, right? So this is what gives us a constant, the Euler character. And then we subtract, again, the square root of gr. But r was already fixed to 2, so that, or to minus 2. So this gives a term that essentially is the area. So here the area. The area of some region. So it's convenient to think for this. Well, this could be done both in Lorentzian or Euclidean space, but let's think of it in Euclidean space. So this is the area within this region. And we can think of this area as the integral of, let's say, a constant electric field. Let's say, imagine we had a constant electric field in ADS2. So if we had a constant electric field, this could be, we could think of this as a term, as an electric field coupling, which we could integrate by parts, and we get Q times the integral along now the boundary of the gauge potential A mu, of a gauge field in ADS2. This gauge field has nothing to do with the original charged black hole. It's just simply a mathematical artifact to describe this action. Okay. So this looks a bit like the motion of a charged particle. Here we don't have the mass term, but in some sense we always have some kind of counter term that is proportional to the length of the trajectory, right? And so we can really think of this as the motion of a particle, of a massive particle in an electric field, where we tune the mass and the charge so that the trajectory looks a bit like this. Okay. I mean, the circular trajectory, so the simplest solution is a circular trajectory. And in the context of a particle in an electric field, you could view this as an instanton for Schwinger pair production of two boundaries. This is not important for, well, this hasn't been important so far, but you can think about it that way. Now, so that's one way to think about the dynamics. This way has the following conceptual advantage. Has the advantage that you can now think of the whole problem in the following way. So you have ADS2 space, which is a rigid ADS2 space. You have a dynamical boundary, which is essentially a particle, has the same equations and the same form solutions as a particle moving in an electric field. You have the other dynamical variable particle in the other side. And then you can have some extra matter in the interior. So the motion of each of all these particles is Sl2 invariant. It takes place in ADS2 and has a global, each of these problems has a global Sl2 symmetry. And you can think of the Hamiltonian of the full system essentially as the Hamiltonian of the left particle, the Hamiltonian of the matter thing in the interior, and the Hamiltonian of describing the right boundary. Okay, so we have three decoupled systems so far, and one represents each of these, and the motion of this boundary reflects the boundary graviton, right? The dynamics of the boundary graviton. Now, this global what is this global Sl2R symmetry? So it represents the fact that we can take this diagram and move it inside ADS2. Okay, but physical quantities should be quantities that refer to, so we define that the boundary time is really the proper time along this trajectory, and if we shift this whole thing inside this ambient ADS2, that's the same configuration, doesn't change any intrinsic relations. And so really we should take this and impose a constraint. So the full system is this plus a constraint. And the constraint is that the total Sl2R charge, total vanishes. So that will be the Sl2R of the left, charge of the left particle plus the Sl2R charge of the matter plus the Sl2R charge of the right particle. Okay? You can view this as the reparametrization constraint of GR, so both the Hamiltonian and some of the spatial constraints. Of course, those are one constraint per point in space, but we have solved some of those constraints. All that remains is this more global part, but still is a gauge, should be viewed as a gauge symmetry, and we should impose this constraint. Okay? So it's really gauge symmetry. It's a gauge symmetry in the sense that we set it to 0. It's not local in the interior, it's just from the point of view, it's like a global symmetry in the sense that it does not depend on the position. The generators do not depend on the position. We don't have one generator per point in space-time. We just have these single generators for the whole space-time. Is that clear? Is this clear? It should be, I hope it's completely crystal clear what we are doing. Yeah? Okay, so that's the story. That's one way of thinking about the gravitational dynamics. So, yeah.
The Centro doesn't act on the proper time of the boundary?
No. This is a purely gauge symmetry. This doesn't act on anything physical. In addition, we have maybe I should explain this a little more. Because this is a point that is confusing, and I should probably explain it a little better. So we discussed before a solution where we wrote a metric that was Sl2R invariant, and a dilaton that was not Sl2R invariant, but was U1 invariant, right? So we would say that metric and dilaton have a physical U1 symmetry. Okay. Good. In this system, that physical U1 symmetry corresponds to shifting the times, the proper times along these trajectories. Okay, so that's it acts on this proper time and it shifts the proper time along these trajectories, but it does not move these whole trajectories in ADS2. That's something else that is done by these other symmetries. Okay. So we should not confuse the physical symmetry of ADS2, of this nearly ADS2, which is that U1 symmetry. It's unrelated to these gauge symmetries. Okay, so here, I mentioned this thing about the particle in the electric field. That's important for doing some concrete computations. But for many qualitative things, the only thing that is important about these trajectories is that they are Sl2 invariant. They have, each one is a Sl2 invariant. And then when you send in matter, the Sl2 charges have to be preserved at this location. So you can think of, so this, the Sl2 charges for the matter is just the ordinary energy and momentum of these particles and blah, blah, blah. And so in this vertex, you have to, in particular, preserve the local momentum, energy, and momentum. So if you're sending some particle, this one will be bent a bit outwards, right? And you'll have a trajectory like that, like what we discussed before. So we can understand this bending from the picture of, let's say, local momentum conservation here. And we don't need to solve any equations. Before, we had to solve the phi equation. So this shows you that this picture is a little more simple. You can understand it more intuitively. And so that was the effect that was saying that when you send in some matter, the horizon moves a bit outwards. Okay, same effect that we discussed before. Okay. Good.
Yeah, I'm a little bit confused.
Yeah.
So this boundary particle,
Yeah.
essentially just the boundary value of phi, right?
No, the boundary value is constant. Yeah.
The boundary value.
Yeah. I gave two descriptions. Yeah, there are two descriptions. In one description, you solve for phi, and then depending on matter, the value of phi depends, and where phi equals to the boundary value is different. Right? So that's one description. There's a separate description, which is this one that I given here. Here there is no phi. So phi was a Lagrange multiplier, was integrated out. It disappeared completely from the description. But we get this dynamical boundary particles. So boundary particles whose location they have a quantum mechanical degree of freedom, right? It's just a particle which, well, formally is the same as the particle moving in an electric field, right? And that's
So that corresponding to the previous location change of the boundary.
exactly, yeah.
But how do I see that this is equivalent to that? I don't immediately see.
Yeah, it's not so obvious. I mean, we derived it formally by looking at, well, we derived it by taking the original action and reducing it to this action, and then analyzing the problem with this action. So we started from the two actions, and we derived the same thing in two different ways, one in each for each form of the action. Yeah, there is yet a third form of the action that we'll discuss later, and each of these forms is useful for something. So it's convenient to have them all in your mind.
Also, how do I directly read the charge of this boundary, Sl2 charge of this boundary particle?
Well, that you have to work a little more. So you start with this description. So one way is to write down more explicitly than I have done the expression for the more explicit than I have done the expression for the charge for the Lagrangian, and then use another procedure to. So that Lagrangian has an Sl2 symmetry, and then you write down another charges for that, and that will give you some expressions.
So you have to do some more.
Well, yeah, that's in principle. That's straightforward, conceptually straightforward. There is a little more sleek way to do it by noticing that, well, all these trajectories are obtained by solving some equations. Like, for example, geodesics in ADS2. There's some quick way to do it by using embedding coordinates, but it's a technical thing that I don't want to. I could, if people are interested, you can ask me at the end.
Just a short question, maybe.
well, the only physical symmetry of the system with no matter is U1. That's the physical symmetry. And it corresponds to time translations. So the Sl2R symmetries we're talking about here are gauge symmetries. So nothing is charged in the whole physical theory. And so it's some symmetry in the intermediate steps of the discussion, but we should always at the end restrict to Sl2R invariant. Okay, so now we are going to talk about something else. So in principle, this looks a little different from what I was discussing so far. So we're not going to start with a particular form of the action, but we're going to start with the metric of ADS2. Let's say written as, well, we were writing it as d rho. Let's say we go to large rho, so we can write this as e to the 2 rho times dt squared, right? And then we will notice that this metric has a so-called asymptotic symmetry. And this makes a little bit of a connection to what Andy Strominger was talking about. Andy Strominger was talking about the asymptotic symmetries of flat space. So here we're going to talk about the asymptotic symmetries of ADS2. So these are symmetries these are reparametrizations that preserve the form of the metric. So if we change t to f of t, and then we change rho to rho minus log of f prime, okay? Then if we insert this reparametrization in here, we'll find that so this is, let's focus first on just this leading term in the metric, and this leading term in the metric will get an f prime squared dt squared, but due to this shift we will cancel that f prime and we'll end up with the same e to the 2 rho dt squared. So we see that we preserve the leading term in the metric, and we can change this a little more just to preserve also the sub-leading term in the metric. I'm not going to do it explicitly. So this is a so-called asymptotic symmetry of the metric, leaves the leading terms in the metric. So when you change the metric, there are some further terms here that are suppressed by e to the minus 2 rho, etc., that we cannot leave invariant, but the idea is that the leading terms in the metric remain invariant. That's so-called asymptotic symmetry. Now, if we, in the original coordinates, we had a boundary condition which was, let's say, if this is rho and this is time, so a boundary condition which was at some fixed value of rho, then after doing this transformation, the boundary condition will be at, would be at some wiggly value of rho that depends on, that depends on what this function f was. And vice versa, if we do this transformation and we take now a straight boundary condition here, if we do the inverse of that transformation, we'll end up with a wiggly line here in the original space, right? So these transformations are changing physical situations which have, let's say, we consider we can now think of these transformations as relating different situations for the boundary trajectory. So if we have Euclidean ADS2 or hyperbolic space, then we had the original, let's say, an original boundary at some fixed radial position, and then this type of symmetries relate them to configurations where we have a wiggly trajectory here on the boundary. Now we should think of the physical space as what lies inside this region, right? And here, so imagine that with a cookie cutter, you cut out this region of ADS2 space. So in this case, we just get a round cookie. Here we get a not round cookie, okay? So it's really different. So if you calculate correlators in this case on the boundary, they will be different. With fields propagating through the bulk, they will be different. So here we have something that relates these two configurations. Okay, so we can think of then these symmetries, f of tau, as or the diffeomorphisms of S1 as being spontaneous. So they are preserved by the boundary conditions. So the boundary conditions do not realize that you've done this symmetry. Okay, so if you have this line or you have the other line, locally the two have the same proper length, and we will not realize that we now go back to ADS2. We have set the dilaton to 0, and so if we do this transformation, we don't realize that we are doing anything. Okay, but globally, these two configurations are physically different, and we should view them as inequivalent. So this is a zero mode of the system. So if we had purely ADS2, we would have, without the dilaton, the original theory we started discussing, all these configurations will have exactly the same action, and so this would be a zero mode of the system. Okay. Now, there are some transformations, some diff transformations, which are leave the configuration invariant, which is the global Sl2 transformation, because we just move the position of this whole piece of the spacetime inside the bigger H2 space. And that doesn't change anything intrinsic. So the goldstones are really diff S1 mod Sl2. Okay. So these are somehow, by goldstone I mean, what I'm meaning here is flat directions in the Euclidean path integral. Okay, so we are doing the Euclidean path integral over all metrics, and we have these particular directions which are flat. Okay, so in some ways, when we are doing the Euclidean path integral, we will have to integrate over this functions f, and we have no action. The action is 0, so it's constant. So this will give us an infinity. Okay. Okay, so that's the reason why we need to go to nearly ADS2. And then when we go to nearly ADS2, then we are putting a new term in the action. And I have the same term that we had before. So we have this new term in the action. And now we are going to treat it in a slightly different way. So we can take that term in the action and apply this reparametrization now to this term in the action. So this is a term that now depends on the extrinsic curvature of that boundary, and when we do that transformation, the extrinsic curvature of that boundary will change, and we'll get a non-trivial action for f. I won't do the computation completely. So that when we do this, there will be some terms. Remember that phi b, we are taking it to be some phi r over epsilon, right? So we're putting the boundary at some big epsilon. And so this whole thing will go like, there will be some term that goes like the length of the boundary over epsilon squared, and then a term that goes like phi r times the Schwarzian of that transformation f, and the proper time on the boundary, which we can call u. Okay. And this Schwarzian derivative has the form f double prime over f prime all prime minus 1/2 f double prime over f prime squared. Okay. Now I won't derive all the terms, but let me just give an idea for why we get so many primes here. We have the metric is supposed to be 1 over epsilon squared times du, and so when we do a reparametrization, we have something like f prime squared du squared, and then we have some cutoff c here, some surface here, and the surface. So we can solve it. We can find c by solving these equations. We get that c is equal to epsilon f prime, And so already C has some f prime, and then when we calculate the extrinsic curvature, we'll have terms that have some extra derivatives, and that's why, so let's say C prime squared, and that's why we get this type of structure. I won't derive it for you in detail, but you can find the derivation in our paper, for example. So important point is that we get a non-trivial action. And you can also say that, well, this is the lowest, we expect to get the local actions because it's a local term. And whatever we get should be Sl2R invariant under this guy. So it should be invariant under this quotient because that's not part of, that has zero action. And this is the simplest Sl2R invariant expression that we can write down, the lowest number of derivatives. Okay. So phi was dimensionless. This has dimensions of length, and so this has also dimensions of length. So this is what in the SYK model was n over j. Okay. So something that has dimensions of some 1 over energy. Okay. So here the dimensions of this factor can be just rid off from the dimensions of this action. So this action has essentially the dimensions of 2 derivatives, right? So there are 2 derivatives in the numerator, 1 derivative in the denominator. We get just 1 derivative squared. So 2 derivatives, 1 integral cancels 1 derivative. They have 1 derivative. And that's why we need to divide by 1 energy. Okay. Okay, very good. Now, if someone writes for you the action, okay, so yeah,
The derivation term is 1 over epsilon or 1 over epsilon squared?
x squared, yeah. So there is a 1 over epsilon that comes from the length, right? So there is an integral of the extrinsic curvature times g, blah, blah, blah. So one of the epsilons comes from the length, and the other one comes from this phi b. That has a 1 over epsilon. That's why we got 1 over epsilon squared.
Epsilon has 1/2 length.
What?
The dimension of epsilon is square root of length.
Yeah, so there is a phi r here. Right. So now it has the right dimensions. Okay. Now, when someone writes an action like this, you should be worried because normally in quantum mechanics, we don't write actions with with many derivatives, more than 2 derivatives. And basically, we don't do that because actions with more than 2 derivatives lead to ghosts and states with negative norm, etc. And the reason this is not a problem here is that we have the higher derivatives, but we also have this gauge symmetry. So this is the Sl2R symmetry we are quotienting hereby, and we should treat it as a gauge symmetry in this action. So it's a gauge symmetry which is independent of time. It's something we could call the global gauge symmetry in the sense that it's independent. Well, you could perhaps make it local also by introducing an Sl2R gauge field. But the point is that we take this action and then we quotient by this type of symmetries. We impose that the charges vanish. So same story we discussed when we discussed the particles in the electric field. Okay. Okay. So now, so f in this action should roughly be viewed as the Poincare coordinate of ADS. And if we want to go to the of Euclidean, let's say it could be Euclidean ADS. If we want to go to the circle, it's convenient to write f of tau as the tangent of pi u over beta. Okay. This somehow you can view this as relating the 0 temperature to finite temperature contribution. This is the same as what Kitaev was talking about, except that he wrote this as e to the I 2 pi u over beta, right? He was considering a complex f. I mean, you don't need to do that. You could consider just completely a real f. The cost of making this slightly more complicated. So if you do this transformation, then you can evaluate that Schwarzian action. on this configuration. So this configuration turns out to be a solution also to this action, and you can evaluate the actual action, and so whatever it evaluates to, it will be proportional to phi r, right? Since we said that the action had two derivatives, we have the Lagrangian will be proportional to two derivatives, so that will be 1 over beta squared. We integrate over beta, that's a beta, so the whole thing then has a beta dividing here. Okay? I'm not writing the numerical coefficients, but we could easily write down the numerical coefficients. Okay? So what is the significance of this action? So this on-shell value of the action is telling us what the near extremal entropy of the black hole is. So we can write it also as phi r times the temperature. So we find that the near extremal entropy of the black hole is proportional to the temperature. Okay. Now, naively, if you were told that, well, we have some system with conformal invariance, and then we break the conformal invariance, the scaling symmetry, you might have thought that the scaling of the near extremal entropy could be temperature to any power related to how we break the conformal symmetry. Right? But here we have a very special pattern of symmetry. So we have this much bigger symmetry group. We can think of these symmetries as being spontaneously broken by the ADS metric, and then further explicitly broken by this action. And this pattern of spontaneous and explicit breaking is what fixes this particular power of the temperature. And for, let's say, ordinary observables, this is the main consequence of this symmetry. For simple observables, we'll discuss some other observables, more complex observables later, which are also a consequence of this symmetry and this pattern of symmetry breaking. Now, this pattern of both spontaneous and explicit breaking. Now, you might think that if the asymmetry is both explicitly and spontaneously broken, if the symmetry is explicitly broken, you might think you have no right to talk about it as a spontaneously broken symmetry also, right? These seem to be like incompatible things. But this is not the case, and in fact, this idea of both explicit and spontaneous breaking, we use it a lot in physics. And so one example from particle physics is the chiral symmetry of QCD. So imagine QCD with two flavors. Then we have an SU2 left times SU2 right symmetry that is spontaneously broken for 0 pi. So when the quark masses are 0, that is spontaneously broken to just an SU2 symmetry, right? And then with the Goldstone bosons of this breaking are the pions, okay, massless pions. But then we can introduce non-zero quark masses, and if we have non-zero quark masses, then the symmetry would also be explicitly broken, okay? And depending on, so it will be explicitly broken, but it's still useful. So the pions are not massless anymore. There will be a special point in this space, in the space of configurations of pions, which is an S3, will be a special point that corresponds to the minimum action configuration, minimum energy configuration. Okay, so here we have something somewhat similar. Yes. 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 Here in this analogy, the symmetry that is being spontaneously broken is diff S1, not this Sl2R, it's just diff S1. The analog of this Sl2R in this analogy is the SU2 that is unbroken. Well, the Goldstone, so diff S1 mod Sl2 is where the Goldstone bosons live, right? So if we want to discuss the space of Goldstone bosons, right? We would it's an S3, right? We could think of that space as SU2 times SU2 divided by SU2. So it's the full global symmetry divided by the subgroup that is left invariant, right? And So if we use that description, then in order to do that division, that quotient, we need to gauge that. We normally don't do that in this case. We just think of it as the final configuration, which is an S3. But in general, that's what we would do, and it's convenient in this particular case to. But some people like not to think of this as a gauge symmetry and just think only about the physical degrees of freedom. So, for example, in Daniel Harlow's talk, he was emphasizing just a completely physical, focusing only on the physical degrees of freedom of this action, and never talking about this this pattern. So it's useful to think about this pattern, so you have the same pattern in the SYK model, and that's the reason why many things agree. Everything that depends on the symmetry breaking and the Schwarzian part of the action will agree between SYK and nearly ADS2. There are some other things that will not agree, so things that are not related to that will not be the same. But, yeah.
Usually you can think of the symmetries as acting on Hilbert space.
Yes.
Here the thing is more Euclidean.
Yes. That's a defect of our understanding. It would be nicer to understand how the symmetries act on the Hilbert space. Yes, that's an important question whose answer I don't know. Yeah.
So is the fact that epsilon is finite the explicit symmetry breaking, or is it something in the Schwarzian term?
No, it's something in the Schwarzian term. It's not related to epsilon being finite. It's just related to the fact of phi growing, right? It's just that phi grows, like phi r over epsilon. Okay. So let me discuss a little bit more explicitly the point I made about the ghosts just a moment ago. So we looked at the this tangent of u, but here we could change this slightly and put this tau of u. Let me see. No, let me write it as tau of u. I'm trying to use the same notation that Kitayo was using. So this is a coordinate tau, which has period 2 pi. It's somehow the coordinate on the unit hyperbolic space. And then we are reparametrizing that. And we can think of solutions of, so we can rewrite the Schwarzian action. We can insert this into the Schwarzian, and then we'll get some action in terms of tau of u. Okay. And there are various infinitesimal solutions of this. So first we have the original solution that we had over beta, right? And then there are, of course, adding a constant is a trivial solution. And then we can add some term linear in u. And then there are some terms that look like e to the iu plus e to the minus iu. So these are just infinitesimal fluctuations around the original solution. So this was the original solution that gave us the near extremal black hole. And then we have these other configurations. These two are related to displacing the black hole and related to zero modes under the. They're related to the action of Sl2 generators on the original solution. Okay. So they are kind of trivial. And then this one represents a non-trivial excitation of the system that amounts to changing the temperature, so increasing the energy of the system. Okay. So in this type of modes, in some situations, they are set to 0. So if you consider the Lorentzian solution, for example, and you try to fluctuate the solution only of this boundary, you will not obey the Sl2R charge constraint, and then the Sl2R charge constraints will set these parameters to 0. Okay? So they do not arise in that case. If you have just the pure gravity configuration. Okay. So if we consider, for example, a time order correlator, so something like where you have two Euclidean, so let's say this line here represents the propagation of a particle in ADS2, and then this is some other propagation of a particle in ADS2. So this will couple to the F mode in some way. I'm going to be very more precise about that coupling later. So this will couple to F in some way. And there will be a gravitational correction where we're exchanging this F. So I'm writing here as a bulk thing, but of course, we could view it as a change in the motion of the boundary, right? Of the boundary particle. So in this case, when we cut here, we have to impose here the Sl2 constraints of essentially the vacuum theory. And then these modes will be set to 0. And that implies there will not be anything essentially exponentially growing in Lorentzian signature when we consider such correlators. So in Lorentzian signatures, this would go like e to the t and e to the minus t. On the other hand, if we consider a configuration which in Lorentzian signature will continue to an out-of-time order correlator, then the pattern of points is more like this. And here, when we are considering interaction, we have a propagation of some object from between these two lines. I'll discuss what that object is more precisely later, but well, it's just some excitation of this Schwarzian. And when we cut here, we can obey the Sl2 constraints more generally because there are all these other trajectories, and we can excite these modes. And that's the basic one way to understand why we can get these exponentially growing corrections in that configuration. Okay, so now this okay, now I'm going to say a few more words on this pattern of symmetry breaking, and so I emphasize that it's useful to think about this pattern of symmetry breaking where we have the symmetry being both explicitly and spontaneously broken. And this pattern governs many things. So it governs one thing is the near extremal entropy, right, that we already discussed. Okay. It also governs gravitational back reaction because it fixes the form of the action, right? This says that the leading term in the action should be the Schwarzian, which is equivalent to the particle in the electric field and the Jakob-Teitelbaum theory. It also fixes the out-of-time order correlators, so we can calculate them. The leading gravitational effect comes from solving this action, and it has the general form we discuss in a gravity theory with the maximal exponent. So this in particular gives a maximal chaos exponent. It's not terribly obvious. I mean, if I just given you this action, well, yeah, I think it is clear. So the reason you get maximal chaos is that when you look at small solutions around the vacuum, you have the precise factor here in the exponent is determined by the Sl2 this Sl2 gauge symmetry, and so it's linked. So it's linked to the beta. Well, I guess if I were a little more precise here, I should write tau, and tau for tau we put the leading order expression for tau. I should put 2 pi u over beta. Okay, and so the fact that this is 2 pi u over beta is determined by the Sl2 symmetries, and so that fixes the chaos exponent. Right, it's determined by the geometry of ADS2 in this case. So it's some. Yes.
Yeah, so that I think seems to be more important for the rather than Sl2.
Well, the reason why when we start with this solution and we act with an Sl2 symmetry, right, we get a new solution which has precisely this exponential form. Yeah.
So that's important, but yeah. but the precise value of lambda.
Yes.
That is determined by periodicity.
Yeah. It's also consistent with the periodicity. Yeah.
Mm-hmm. Right. Yeah, but if you don't impose periodicity,
yes.
you can have other with L2R.
Yes. You can have other things, but in a Euclidean theory that is based on a single variable like this, you will not get that. It's incompatible with the Euclidean theory. Yeah. So if you're going to start analytically continue from the Euclidean theory, you'll have to understand why you can get some different period. Exactly. And then another thing that we'll probably discuss next time is wormhole traversability. also there are many interesting effects related to wormhole traversability and teleportation that depend purely on that. Okay. So now I like to spend the remaining few minutes explaining a little more in detail how we use this Schwarzian action to do computations like this one here. Yeah, maybe I should keep these diagrams. And I should, so the idea is that we start first in the 0th approximation. We start with particles that propagate in ADS2, okay, in a completely rigid ADS2, and then we couple them to this Schwarzian mode F. So, for example, let's imagine we consider a 4-point function. For example, V1. The indices denote the times, W2, W3, W4. So V and W represent two different fields in ADS. So there will be two different fields. So to leading approximation, this will be computed by taking the 2-point function of the V and the W. So that to leading order, this will be just V1, V2, W3, W4. And then this, if we were in Euclidean space like this would be just the conformal invariant expressions for these correlators, right? So in particular, for example, this one would be something like 1 over sine of tau 1, 2 over 2 to delta, for example, where tau is the variable that has period 2 pi. That's one way we could get this answer. And this is, of course, also the result of taking this is simply the result of taking something that looks like F1 minus F2 to the 2 delta. So that would be the zero temperature calculation is the dimension of V, the dimension of the operator V. And then we do the transformation with the tangent that we discussed before, that I erased, and then you get this expression. Okay. Now, in the next approximation, what we are going to do is we are going to keep essentially the same form of the correlators, but we're going to do a reparametrization of these correlators. So what we're going to do is we're going to change, we're going to consider this asymptotic reparametrization, or change this trajectory of the boundary and so on, apply this function f. And what that does to the correlators is it does a reparametrization of the correlators. So it changes, so we think of that as f1 of u minus f2 of, well, f of u, let's say 1, there is a single f. Let me write bigger because I'm going to make a mess otherwise. So we take the original correlator and we act with the reparametrization f. Okay. So what that does is it. So we have f, which is just some function, f of u2, f prime of u1, f prime of u2. Okay. To the 2 delta. Okay. So before, when I said that we go from this to that, we are just I'm referring to that. If you put here the tangent of u, you get this sign. Okay. But in general, you can put something that contains some additional function. Okay. Okay. This is, if you wish, how the correlator changes when you consider one of these wiggly boundaries, right? So the correlator changes because you are this f primes comes from the fact that you are moving either closer or further from the boundary, and that just reflects the scaling of the correlator. And then these functions reflect the fact that now the times at which the proper lengths at which they are evaluated are different in the two solutions. So they are the same in the background space, but the proper length along this curve is different, and that's what this dependence here reflects. Okay, so then you can you can take those expressions and think about the gravity. So this just reflects the gravitational correction to this 4-point function. And you can write it as the integral df of the Schwarzian action that we wrote over there. So phi r Schwarzian f of u. And then you insert for each of the two correlators, you insert the expression f and the similar expression for w, right? So we have the same two expressions. And in principle, if you did this functional integral exactly, you would get the full gravitational correction. But of course, we think of this term here as being large, right? I mentioned that at least in the connection to the SYK, we have n over j. But we should think of this as scaling like 1 over g Newton. That multiplies the whole action. So in the classical regime corresponds to the regime in which this phi is very large. And there we can do a quadratic approximation of this action around the minimum, right? So we can expand the function f. So we say that f is, let's say, the tangent of well, we could say it's tau of u, and then this is, for example, 2 pi u over beta plus some epsilon of u, right? And then we expand in epsilon. We expand in epsilon everywhere. So we expand in epsilon here, we get something quadratic in epsilon. We expand in epsilon here, we again get some sources. The leading sources will be a term linear in epsilon here and a term linear in epsilon here. So in the end of the day, we are going to get an action which has the form. I'm going to set beta to be 2 pi. I'm not going to want to keep track of all these factors of beta. So we have a functional integral d epsilon of e to the minus this phi r. And then we have integral du. There is a term epsilon double prime square minus epsilon prime square. And then two sources that are linear in epsilon. So some linear operator acting on epsilon that depends on points. Some linear operator that depends on points 1 and 2 on epsilon. And some other linear operator that depends on points 3 and 4 acting on epsilon. I'm not going to write this very explicitly. It's not something very complicated. This is something like epsilon prime at position number 1 minus epsilon prime at position number 2 plus and so on. It just simply comes from expanding this expression. So the first two terms I wrote come from expanding this. And in this way, you can calculate then the gravitational correction to the 4-point function. So before I was writing these diagrams, which contain some kind of exchange between the two double lines, what I really was talking about was precisely this. So this is a Gaussian action. You can invert this, get the propagator for epsilon, and then evaluate this 2-point function. And in this way, you can calculate the time order correlator, the out-of-time order correlator. You can do whatever calculation you want. And the physical, so in addition to this, there could be other terms in the correlator. So there could be direct interactions in the bulk. So the bulk could have some other field. Let me denote it by dotted lines. Let's say there is a massive field in the bulk that leads to an exchange, some extra diagram like this. Well, that is not included in this Schwarzian action discussion. So we're not including that. So that's some extra 1 over n correction. We don't expect this extra 1 over n correction to grow, to lead to chaos and so on. It might in some cases. But if these fields have higher spin, for example. But if these fields are ordinary scalars and so on, you don't expect them to give rise to chaos. So that's why we don't include it in that configuration, that discussion. There is another reason for thinking that these are subleading, and it's the fact that when the dust settles here, we'll have here terms that go like phi r over beta. And so for large beta, this coefficient can be small, right? And once you do this computation, you get that this particular term in the 4-point function is some function of the times. And there is a factor of beta over phi r, right? So this is like g Newton times beta roughly. And so these terms are enhanced at low temperatures. So if you did an exchange here in the bulk, this configuration this is happening inside ADS2. That will be a completely scale invariant function of the times, and so there will be no beta dependence. While here we have that these terms are enhanced by this extra factor of beta. Okay. So if we have an n counting, like let's say SYK type thing, then both this correction and this correction are of order 1 over n, but here we are saying that this correction is like n over, the n is in the denominator times beta j times this function, while the other corrections would be terms that go like 1 over n. Okay? So these terms that come from this, from the Schwarzian action are enhanced by a factor of beta j. So in that sense, they are the leading contributions. Well, I think I'm done. Let me see if I some closing comment. Well, let me try to summarize what we said today. So we analyzed in great detail the dynamics of this nearly ADS2 gravity, and we saw 3 descriptions for it. So one was the original Yakib-Teitelbaum type action with the phi and the metric. The other was the discussion of, we are in completely fixed ADS2, and we have the trajectories of the boundary particles that are quantum mechanical degree of freedom living purely on the boundary. And then third, we discussed this description where the boundary, the dynamics is characterized by this Schwarzian action. And this brings out the connection most clearly to this broken diffeomorphism invariance. That's the advantage of this, and leads to some simple ways of coupling so that one of the advantages of these variables is that it simplifies the coupling between the matter in the bulk and this boundary and the boundary degree of freedom. So you can immediately write it down in this way. So that's the advantage of this one. So they all have their own advantages. Has some disadvantages in the sense that they have these extra higher derivatives and so on. Okay, so next time we'll discuss further physical effects that are related to these actions. And one final point I didn't discuss in great detail, maybe I'll discuss a little bit more next time, is that there is a connection between the SYK model and this that goes through this common pattern of symmetry breaking. Let me emphasize a bit this point. So people have noticed, well, for a long time that ADS2 might be related to some CFT1 and have tried to propose some examples. Like for one popular thing was this supersymmetric Sl2 invariant quantum mechanics of Fubini, Alfaro, Furlan, etc. I'm not sure if you don't know it better. So those systems have an exact Sl2 symmetry, and they do not display this pattern of symmetry breakings, this diff S1 and so on. They don't have that, and so in that sense they are not they don't display the symmetries of ADS2. They don't expect them to be dual to ADS2. They might describe the motion of branes inside some ADS2, and they do that very well, but they don't have the right symmetries to be the full dual, gravity dual, the full dual in the sense of ADS-CFT to an ADS2 or nearly ADS2 geometry. In particular, they are exactly conformal invariant, and here we derive the fact that you need to break the conformal symmetry slightly in order to have a sensible theory. So if you haven't heard about those, good. But they will become important for something else. But any other questions? Yeah.
So in SYK, there was disorder and disorder
Yes.
averaging.
Yes.
Is there something playing similar roles here?
No. This disorder was a technical thing that simplified the calculations of the model and made the model solvable. But you can have the same physics of SYK from the so-called tensor models. So you can write an action without disorder, whose leading order diagrams are the same as the SYK ones. Some things with disorder are simpler, but also less clear. So because you're having this disorder, the fact that you're ensured to have a Hamiltonian interpretation is a little less clear when you do the disorder average.
Because that integral looks a little bit like averaging over this F mode.
Yeah.
That's what you would do when you do this order, but with a different weight.
Yeah, in that sense it's similar, but yeah, it's not related to that because we will have the same mode in these tensor models. And here we started from an ordinary gravity theory, which with the Hamiltonian and so on. So, I mean, the talk of Dan Harlow emphasized a lot the Hamiltonian Lorentzian interpretation. This, and so you can understand that clearly. No, notice that we have here, I mean, one important point is that here we had this infinite number of degrees of freedom of F. They were all off-shell. So the number of on-shell degrees of freedom that this action describes is small. It's just the quantum mechanical degree of freedom. And the only physical thing is just changing the energy. So this whole discussion is about essentially energy conservation and energy fluctuations. That's one part of it. And that's especially when we were talking about the solutions, the part that was linear in U. And within the same action, you're also describing this, you could call them the shockwave modes or the modes related to chaos that grow exponentially in time. So they are part of the same structure in this case. Yeah.
So in higher dimensions, Schenker and Stanford, they computed the stringing corrections to the numbers.
Yes, yes.
Here the square seems it would be a bit different because of this beta enhancement.
Yes.
Is there an intuitive way to think about this?
I don't know. Well, let me say that so here we use very little properties of the theory in the bulk, right? We use just this pattern of symmetry breaking. In particular, the theory in the bulk could be a string theory with a string length which is afforded the radius of ADS. And then this symmetry resonance would still be valid, and we still would have the maximal exponent. And then you could ask, well, but didn't I expect to have some correction? I even talked about that correction before. So what happens in this case is the following, that you can indeed compute the correction to the Lyapunov exponent for a nearly ADS2 geometry when, let's say, the string scale is small. And so you find that lambda, so it's the maximal value, so let me say 1, right? And then there are some corrections which go like, in general, you expect them to go like L over radius of ADS. This would be the naive guess, right? But it turns out that there is a further term that is, I'm going to call it delta S over S, where this is the near extremal entropy and this is the total entropy S0 of the extremal black hole. So there's an extra suppression factor. This is just by computing straightforwardly the string correction for a near extremal black hole. So you find that you find this expression. So you see that when we approach extremality, we get a very a correction which is more suppressed than you naively expected. And this is consistent with the idea that the dynamics is determined by the symmetries, and if you have this diff, spontaneously broken diff symmetry and so on, you get the maximal chaos.
This is very surprising though, because in higher dimensions, you have LS equals LADS, and you get 0 chaos.
Exactly, yeah. Yeah, this is strange. It's a strange property of ADS2. And this follows from a straightforward calculation. Yeah, I should probably have a better argument for why you get this formula. Well, I guess one argument is the fact that, one argument is the argument we've been saying that this maximal exponent is determined by the symmetries of the problem. But, yeah, so why the correction is further suppressed, I'm not explaining. Well, I guess one thing one could say is that in 2 dimensions, this gravitational degree of freedom is very delocalized, right? You can, in higher dimensions, the shockwave mode is at the black hole horizon, and it's sensitive to the black hole, to the stringy corrections, right? Because you have the shock waves, they are very small, and if there is a finite string scale, they will correct them. But here in ADS2, the mode is very delocalized. It's even, we are even representing it as a boundary mode. So you could view it as existing, having a wave function which is constant in ADS, if you wish. And so it's less sensitive to the stringy corrections. It's very big, and the stringy corrections, it's a mode that is much bigger. It's many, many ADS units, right? And it's that overall size that determines make the stringy corrections irrelevant, or make them particularly small. That's a more direct argument. But, okay. Any other question? Yeah.
So when you have an empty ADS, you can understand it when you want to some embedding for higher dimensional black plus consider this jacket later down
Yes,
as
yes.
some expansion of this some Piloton gravity model that we get by
Yes.
dimensional reduction.
Yes, good, yes.
Right, and okay, so there, can you understand like the finite temperature Lorentzian diagram that you wrote like with the alternating phi plus infinity minus infinity?
Yes.
So it really looks like Reisenhower.
Yeah. It just comes from the original. I mean, yeah. So I described it in 2 dimensions, and it has the plus and minus infinity and so on. If you embed it in the higher dimensional space, you get a slightly modified diagram, right? But it contains the gross features are such that the regions with phi equal to minus infinity are the singularities of Reisner-Nordstrom that are time-like. It's a whole discussion that in in general you expect the singularities not to be time-like, but to be maybe either null or space-like. But I won't get into that.
So there's no like ADS to so like there's some ADS to region in non-extremal space-time.
Yeah.
As you approach the horizon, it becomes similar.
Well, I mean so when we draw this Penrose diagram, right? So we're drawing this Penrose diagram for the. So this whole space here, this strip is ADS2, right? And then in this near extremal black hole, we are exploring. The exterior of the 2 black holes are these 2 regions. We also have this region in the interior. And in principle, we continue an infinite number of times. That is not well understood, how to interpret the rest, or where there's really a singularity here. That's not clearly understood from the boundary point of view or in the full quantum theory. The distance between here and this boundary is when you approach extremality, it grows. So it's many, many ADS units. Right? The region where you have Rinder is within distances less than one radius of ADS. Right? So probably a more faithful representation of a situation where it is close to extremality is where this line is very, very close to the boundary. So that would be just a direct diagram, but it's hard to see. So that's why I exaggerate the position of this line, right? Yeah. I'm not sure if that's what you asked, or maybe. Now, in my talk in the workshop, I was talking about a system where you start, and we'll talk more about that later, where we start coupling the 2 sides, and then you start seeing more of this strip. So these 2 horizons separate along the time direction and allow the wormhole to be traversable. So we'll discuss those features next time. Any other question?
Okay, let's thank Juan.